Hey everyone, welcome to Unit 3. It is week 3 of our 5-week class. During this recording, I'm going to cover 4 chapters, chapters 5, 6, 7, and 8. And this is where we're getting kind of the meat of the data mining and indexing of data that we've got in our data warehouse or our data systems. So chapter 5 will be data mining, kind of the overall concepts and constructs inside there. Chapter 6 will be some of our predictive modeling, where we take that data and kind of try to represent what's going to happen in the future. Remember, a model is a subset of realities. We're not going to use all of the data necessarily. We'll take some key elements of the data and try to forecast out. Chapter 7 deals with text analytics, where we have text-based information, whether it be in a Word document or whether it be in a text file or some document that has text in it, try to organize and make sense of it. And then Chapter 8, I find kind of interesting, is web analytics, where we go through and try to analyze search engines, working through how Google PageRank works and through kind of how other search engines get their results on how valid they can be. So I'm sure some of this would be pretty interesting for most of us, but it's kind of good to see the background on how these technologies came to be, and something we use pretty much every day, whether it is something that's text-based or web-based. I'm just kind of understanding the background behind that. So with that, we'll begin. Alright, so chapter 5, I'm going to begin with a data mining chapter. I'll use the PowerPoints that came with the textbook. I did delete many of the slides that were, well, I think they're extra fluff, so with the case studies that are in there, as well as opening vignettes, so you'll notice those slides are missing from this deck here. Starting to go through the book and read those and kind of go through them, but just know that I've omitted them from this presentation. So to begin, we're going to go through our objectives, going to go over and define what data mining is, understand some of the technologies and the data mining processes, kind of the major ones that are in the environment, what the steps are for that. We go through some of the software tools, whether they're paid for commercially, whether they are open source and free. And then at the end, we'll go through some myths of data mining towards the end of this presentation. So why do we even bother with data mining? What's the point? Obviously, we have lots of powerful computing technology these days, and really the driving force behind why we do data mining is business is extremely putting a lot of extreme pressure on leadership in business to become competitive, and they use intense competition at a global scale, which I think is completely right. You'll see that almost every company on some level uses products on a global scale or competes on a global scale, whether it's with employees and labor, whether it's from parts and equipment, whether it's a shipping, whether it's just working with through customers. It's not very often anymore that a company works with only onshore customers or vendors and employees. Usually there's a variety from all over the place. So in order to respond to this intense pressure, we have to use data to our advantage. Another reason why we use data mining is this recognition of value. The recognition of the value in data sources. That means in the past we may have had disparate data stored in different systems, not at all connected together, with no real way to tie it together. A human couldn't look at the various database systems or paper file systems or document repositories or websites or intranets and kind of figure out any patterns between that. Whereas now we understand that all that stuff can be tied together and should be, for the sake of can take advantage of this technology. The last bullet here I want to also mention movement towards conversion of information resources into non-physical form. We've used to have file cabinets full of invoices and full of customer data, employee data. A lot of companies are moving away from that just for the sake of searching. If you can remember back, well, at least when I was younger anyway, we had a microfiche, and we had other microfilm types of libraries, systems in our school library. Can you imagine how difficult that would be to search by hand? Now, the other question is, how do you make a backup of that, besides making a copy of all of the film or all of the microfiche systems? So those technologies are good because it saves space. They were very hard to replicate, certainly very hard to search. To tie things together, you had to really know how to use the most manual things possible to find the data. Whereas we have all these non-tangible, all these non-physical data sources now, we want to take advantage of them. That's really the major point of this. The bullet right above that, exponential increase in data processing and storage capabilities, we certainly have all of that available to us. You can imagine even a few years ago for your own computers, if you had 2 gigs, 4 gigs, 8 gigs of RAM, and maybe a couple hundred gigs of storage space. I remember getting my first 1 gigabyte hard drive and thinking that was just a ginormous sized hard drive. Where now 16 gigs, 32 gigs in a desktop is pretty normal these days. Having a couple terabytes, 2, 3, 4, 5, 6 terabytes storage in a regular desktop computer, that alone kind of tells a story of where we're on for a velocity. So certainly the technology has gotten better, faster, and a lot cheaper. That's also gone true to the enterprise level. Certainly you're not going to buy a 6 terabyte hard drive for a server at the same cost you would for a consumer, but it has gone down considerably in compute horsepower as well as RAM capacity as well as storage, even on the SAN level. So you can get lots more terabytes of data, lots of compute, CPU and RAM for a lot less money. So with that, we can certainly take advantage of looking at these larger data sets and making those associations and looking through that. So going through a definition of what data mining is, there's a couple of key words in here, so we'll focus on the second bullet point here. It's a process, meaning that it's a kind of beginning to end. There's a layout, there's an order to it. Non-trivial means that it's not just some random, not just some unorganized. There's a very specific way to go about this. It's valid, so it's the truth. It's not invaluable. It has a valid way to go about this. It's novel, meaning it's interesting. It has some context to it. Potentially useful and understandable. So I want to pay attention to potentially useful. So you can certainly do data mining and find some very useless things out that are not going to be helpful for the business at all. But certainly you can sort through that and get to the good stuff. So other names you might see, and this might be for if you're looking through the job listings, you might find other words to describe what data mining is. If a position list, knowledge extraction, pattern analysis, knowledge discovery, yada, yada, yada here. What we're really trying to do is make sense of non-structured data. That's kind of what data mining really comes down to. So this is a nice little diagram that kind of puts together some of the constructs inside of data mining. And so really to do a good job of data mining, all of these things kind of come together. So that's why the red, orange kind of in the middle is where it all kind of comes together. So there certainly is some statistical models. So there's certainly some math behind this. We're not going to focus much on the formulas or the ratios much in this class, but certainly know that there's a lot going on behind the scenes. It wouldn't be possible to do all this math without some major compute horsepower behind it. And so with statistics comes modeling, which is that mathematical modeling on there, as well as pattern recognition. They also have some AI, the artificial intelligence, on the right-hand side, which comes into machine learning. So you can kind of teach a computer which has certain lots of logic but doesn't understand how humans think. You can teach a machine to think like a human. Then you've got these information systems and some management science behind that, and that usually comes from databases. And whether they are SQL or Oracle or some other structured database or some other data mart or some other data warehouse that might be out there, all these things really kind of come together, and that's where data mining can really do the most good when you have a lot of this good information put together. So data mining usually comes from a consolidated data warehouse. It doesn't have to, though. I've seen data mining come out of just web server logs. That's not impossible, but usually you want to have at least a data warehouse that has a couple of different input sources where you have really the most value for a company. Usually the data mining environment has a client server, meaning you have a back-end system, and then you have a front-end client or a web client on a PC or a tablet. Usually it's web-based, so you can kind of go in with a browser, so you're not really having to install that client as well. So it kind of depends which system you want to use. So certainly number 3, the third bullet here, data is the most critical ingredient, which may include soft or unstructured data. So probably back in the database classes we had data, which is unsorted, unfiltered, it's raw. Then we have some information, which usually kind of was the next step up from raw data, where it is semi-structured, and you can usually kind of categorize it as been filtered. It's not quite as raw. Then there's knowledge, which really is kind of the place that you want to be. So data mining is kind of that process of walking through and filtering and organizing and going through all of that to try to get to knowledge. And sometimes you can come up with some pretty surprising results, and that's really where the interesting stuff comes from. And really the whole point is behind all this is, again, to help a business go through and compete at a better level, to find patterns with customers, to find patterns with vendors, to find patterns with, where's the best place to open a store, where's the best place to close a store. Certainly Target, the company Target, where they decided to close the pharmacy and outsource that to CVS. They did that certainly with a lot of data. I can tell you that they found that it wasn't profitable, or they couldn't turn enough of a profit to make that worthwhile, so they basically sold that pharmacy business to CVS. Well, it wasn't done just by some manager thinking it was a good idea. They did it based on some data. And I'm betting, in other words, I would bet the farm that they did some real data mining and analysis on that. So the next bullet here is a good piece of information. The miner, the person doing the data mining, is often an end user. So someone who without a data science background, without a mathematical degree, a master's degree in mathematics or something like that, is often an end user. They're looking for some specific association, looking for some piece of useful data to make a decision. And again, is it to launch a product? Is it to open a store? Is it to put products of a certain type at a certain store? Is it to target a certain demographic? Is it somebody in certain neighborhoods or certain zip codes, certain area codes, however you break it down, to launch a product? And all that can come through to an end user that doesn't have a whole lot of mathematical background. I remember a couple of slides back we had that diagram where it uses some mathematical statistics and other AI to help do this. It may not be someone with that kind of a degree to do the actual mining itself, because they're meant to be easy to use. They're meant to do that in the background. So here we have data of all different types. So if you remember a couple of slides back, again, we had data warehouses. Usually it may be the main source, but certainly can come from any collection of information, any collection of data at all. So it could be experiences, observations, experiments, and that's the most scientific way to look at data, where you have, you're running an actual scientific test, you're taking measurements, you're doing readings, you're recording all of this to get a certain result, or to hypothesize and come up with a result. But you may also find data in numbers, words, images, etc. So like a catalog is a great place to do data mining. You kind of find associations there. So data is the lowest form of abstraction, and here we're using the context of abstraction from which information and knowledge are derived. So it's that, again, that lowest unstructured, unfiltered, kind of raw data, and we want to make some sense of it. So what does it actually do? So again, we're looking for patterns in the data, and it could be some kind of a relationship amongst all of this. And so there's a number of types of patterns. We'll go through each of these: association, prediction, cluster, and sequential, to find out how these relationships actually interact. So this diagram kind of goes through so between prediction, association, and clustering, these different techniques, how this might work, and how much direct interaction and which algorithms might be used for that. I'm not going to focus very much on this slide other than to just look at some of the algorithm names. So these are, again, very mathematical, very computationally heavy in nature, and the end user doesn't really care about any of this. They just want to get to the end. I just want to expose you to some of the names of some of these algorithms. And we'll go through some of these k-means, and we'll go through the ANN and SVM on the future slides and the future chapters in this week's lecture. So we'll get through this. So I just want to give you kind of a summary table of all of this. So a couple of tasks we might have here: time series forecasting. So can we spell out, based on the previous data, can we forecast out forward, over a course of weeks or months or years, on how, based on what we've seen so far with the data we've got, can we forecast out? And usually that's possible. Visualization is also something that is an output usually of data mining. This might be a cluster diagram, which is one of the types we got to in just the last slide, where it kind of puts the data on a plot. You can just kind of see where everything kind of clusters together. Well, it's nice, pretty visualization, but it's also some math around that. And if we'll do some of those K-series diagrams, I'll show you that in just a couple of slides as well. So a couple of types of data mining: hypothesis-driven as well as discovery-driven. So hypothesis is, there we have a thought, a notion that something's going to happen a certain way. We hypothesize that to be the case, and we format the data, we look at the data, we formulate what we've got to try to drive to that and prove it whether it's true or false. Now, the other type is data discovery, discovery-driven data, where we discover something that we didn't expect at all. We had no idea what that was going to come about. So both are valid, both work, and just kind of depends on how we want to go about our methodology and our science here. So a couple of classic cases for data mining, customer relationship, and I suspect all of us have experienced this from different companies that we work with or organizations we work with. Many times we will be targeted, and where I live, it's Charter and CenturyLink. They target customers, or they target current customers that have a certain level of service to buy more. So it's the add-on, the bundled service from Charter, or if you got DSL from CenturyLink, they want to add on a phone line or long distance, or they want to bundle in some other cellular service, whatever they've got. They also want to just make sure they're in front of me, so they talk about churn analysis. So how often do I have to send a postcard out or send out something new about the company to make sure I don't switch to another company for services. Likewise, that cross-selling and upselling is that maximize customer value, and identify and treat the most valued customers. So basically we can say who, if I was Charter, who spends the most with me, whether those business accounts or personal accounts, who spends the most money, where do they live, is it a certain neighborhood, do I want to treat them differently, do I want to give them a different level of service? Well, certainly you could use data mining to find out who those best customers are. Put a little check mark in their account, have a little VIP check mark, and if they call in for support, they go to the front of the queue, and they immediately get that better. So that's not illegal. That's certainly possible. In some cases, it may be, to Charter's advantage to do that, to keep them as good customers if they spend the most money. So, but all this can be done with data mining to find out who those customers are, to find out, again, how to bring attention to them, how to upsell to them, how to avoid churn whenever possible. Likewise, the banking data financial, this is going to go back to what I was talking about LexisNexis and my friend Jesse, who's a data scientist over there. All kinds of financial institutions use risk models to determine someone's propensity or someone's capability to pay back a loan or take out service, or to are they a credit risk or not. So you think about purchases that are you think about Fingerhut, the catalog company. Their entire business is based on financial risk models, and they had it very, very good at this, where they say, you can make 3 easy payments of $33 or whatever it is. It's a $100 piece of equipment. It's a $100 toaster, whatever it is. But you make 3 payments. Well, they're actually taking a credit risk on that person, so they have to make sure what your payment history like. Have you made other payments to other vendors? Have you made other payments to Fingerhut? Have you been late on anything? So they can model all of this stuff with data mining, and then they can know if it's legitimate or not. Likewise, they can upsell. If you can afford more per month, how many $33 per month payments can you afford? Can you buy 5 of them, 5 different products at whatever that monthly cost is? So it really makes for an interesting case when you deal with customer risk like that, whether it's loans or whether it is a credit application or whether it is a product-based system like Fingerhut has. Kind of good uses of data mining. A couple more examples here. I'll just kind of breeze through these. Retailing and logistics. I know that Target, I mentioned those guys, really do a lot of data mining because they use their shopping cart, their cartwheel application on your phone. Whenever I walk in Target, my phone chirps at me and lets me know, hey, here's the deal that's going on right now. Better walk over and get it. So it's intentional. They know who I am. They know what I've bought. They know what I'm likely to buy based on the things I've bought in the past. So it is kind of spooky as a customer to have Big Brother watching me. But oftentimes the deals are pretty good, and I'm willing to sacrifice a little of that privacy. Me as a consumer, I'm willing to sacrifice some of that privacy to get some of those good deals. So sometimes it's worth it. Sometimes it's just freaky. I just want to turn it off. So I'll be honest, it's that way too. But in so many cases, whether you use a gas station loyalty, whether you use a Sam's Club card or a Costco card, it's all the same thing. They know what you buy, when you buy it, how much you spend. They can treat you differently, better or worse, based on your levels. And then they know, if you shop there and buy this often, they can kind of predict, your shopping and what inventory levels are necessary. So it's completely meant to, again, drive their business ahead of a very competitive market. Data mining with manufacturing and maintenance, they're talking about working through predicting machinery failures. So if you've got, I have a manufacturing client of mine, and they've got a number of embroidery machines. I mean, there's like 12 of them in a row. And so they can collect data. I know that their vendor does, the company that sold them the embroidery machines, they can pull logs and look at maintenance records there, and they kind of know how long a machine will last. But it's not just because of this one customer. This is from all of the customers that this embroidery machine manufacturer has. They know when the parts are going to fail. They know kind of what the signs are, whether it's a wear and tear, whether it's any anomalies that pop up during the process. Any of that stuff is what could be assigned for maintenance, and then as they gather more data, they know more of when that's going to likely to occur. So some more cases here. There's all kinds of places where this can happen. I want to focus on insurance just for a second because it's a super case for data mining. Life insurance is absolutely 100% based on data mining. If you've ever bought, and I hope you do have life insurance, whenever you have marriage or a house or kids, the things that are of value, life insurance is obviously that the policy that you buy in the event that you pass. Well, how much do they charge you? Well, if you have a terminal illness, obviously it costs a lot more because you're more likely to die. If you are pretty healthy, if you're older, if you're younger, if you're male, if you're female, if you're all these questions that they can ask. Well, why do you think they do that? Well, of course they do. Now, it'll happen when I bought homeowners insurance, one of the questions was, do you have a pool? I put the big, no, I don't. Do you have a trampoline? No, I don't. That should be a sign. Those things jack up the rates because they know people with pools and trampolines, the rates go up because they're more likely, a higher propensity to have a claim. And so insurance companies, life insurance and casualty insurance, life and casualty, both have actuaries, which are people that run math and stats all day long, actuaries that run these models and find out, well, what's the likelihood you're going to die? If you're 25 and healthy and you're female, you're probably going to be very unlikely, so the rates are pretty low. As you get older, if you could become sick, have certain types of medical things happen, you're more likely to pass, so the rates go up. So because they want to do is they want to not pay out any more than they have to. They always want to take in more than they pay out. So perfect case for data mining. All right, so they show a couple more applications here. Let's go down here. Yeah, so there's a number of best practices and standard processes that go about for data mining. And we'll go through some of these. And again, I'm not terribly concerned about the exact way each of these works. I just want to expose you to some of the terminology so you're aware of it. So the first one is the CRISP DM, and it looks almost like SDLC, where we have business understanding, data understanding, prep, modeling, testing, and deployment. And so again, it looks almost like SDLC, where you can, the software development lifecycle, where you try to do your initiation, and then you try to do your project, you kick off the project, do some initial interface with the business and get kind of what the facts are about that. The same thing happens with the database model as well. So looks pretty similar to that. So here's the steps kind of spelled out. And note that the top three account for 85% of the total project time. So it can be a lot to get to that point where you're actually building the model and rolling it out. So kind of interesting. So here's where that front end, that data preparation, one of those first couple steps there, takes so much time, because you really have to get your data consolidated and cleaned and transformed and do any reduction there. So this is, I think, was that step 3? Let's see. Yeah, step 3 here. So this is that whole step 3. Lots and lots of work going on here. And this is where we said unstructured data, that unfiltered, it's raw. Here's where all that stuff gets cleaned up. So just kind of look at what's going on here. If there's a value out of place, if there's missing values, you got to get all of that stuff kind of cleaned up, get the noise out, eliminate inconsistencies. If you've got any outliers and it doesn't really match, doesn't fit at all, that's all got to be kind of cleaned up. Then, if you remember from the database class, we talked about normalization. So this step, looks like step 3, data transformation, normalizing it. That's where you start reducing it. We try to do any duplicates, get it out of there, and then. Yeah, so there's a lot of work that goes into this to get everything kind of cleaned up from this prep task. So this is another process that's different from the CRISP DM. This is a SEMA DM process, and it's similar but just slightly different. And I'm mentioning these processes because different applications may go about it differently. Different companies may approach it differently. Just like you have Waterfall, you have Agile, you have RAD for SDLC. You may have these different processes for data mining as well. And it may even be a hybrid of some of these, frankly. So again, it's fairly similar. We have a sample, explore, modify, model, and assess. And again, this is kind of a SDLC model where you kind of keep going around in a loop to get what you're looking for. All right, so classification is another method that you could use here. Here's some of the interesting facts about it. So yeah, you can read that. It's in the textbook, same thing. All right, so here's some of the reasons we might do this. So the assessment method has these as a capability. So it's robust, it's scalable, it's easy to interpret, or easier to interpret. All right, so here's where some of the math comes in. And again, I'm not terribly concerned about knowing or memorizing this math, because we're really not going to get that deep into it. Let's see if I want to mention anything here. Yeah, so you can apply this type of a graph to any of the previous methods, and we just get some ratios here. And obviously, we want to have more precision generally. Well, I guess it does vary a little bit, but we want to have some precision generally when we've got looking at the data to analyze. All right, so in this case, we're going to do some estimation. Some estimation. You just basically, because if you've got terabytes and terabytes of data, you may not have the computational power to look at all of it. So you just have to basically take some out. You just basically split it out. So we do some testing data and some training data, split it out, and then basically do it in chunks, essentially what happens. So the training data kind of sets up the environment to understand how complex it is and create your model. The actual test data, that's the data you actually put into the model, and then you actually run it through and get your prediction through there. All right, so in this case we've got k-fold cross-validation. We've got k mutually exclusive subsets, so that might be 3, 4, 5. Each subset is used for testing. We go through the experiment k times, so if we've got 3, we do it 3 times or 5 or whatever it is. Then we aggregate the test results for true estimation. Estimation. Gosh, I cannot say that today, sorry. So basically what we're doing is you may not be able to get all of it done in one pass, so you basically just split it up into subsets and just do each of them in regular fashion. There's other estimating methodologies as well, so they list them here. And again, it depends on the size of the data set, how much this you might do. And if you've got 10 billion rows of data, you're probably not going to process all of that. So you may have to do a little bit of estimating based on some samples. So here's where you get some of that sampling and estimating done. All right, now I'm going to go into classification, and here are several types of classification techniques. There are some of these we're going to go through, and some of them make more sense in certain situations. But again, we're not going to dig in that deep to this. This is just going through some of the high-level some terminology, and we'll go for that. So decision tree is the first one for classification. We divide and conquer. It goes through a training set until the division consists of examples from a single class. So basically, whether you grab a sample of data and you keep recursing all the way through it until there is a single class when it's all done. Okay, let's see. There's a couple different types of decision trees. You can change it out on how you split it up, the splitting criteria, when you stop building the tree, so the stopping criteria, and when you do the pruning, or if you do the pruning at all. So again, there's other algorithms you can use inside there, and I'm not even concerned about the algorithms for the sake of this particular course, but decision trees can be a pretty good tool. Again, you can kind of tweak the knobs and the dials a little bit to suit the type and the quantity of data that you've got to make it fit with your analysis. Here's a couple other splitting criteria, piece of information. You can use the Gini index or the information gain to kind of tweak that splitting criteria a little bit. And again, I'm not an expert as far as when you would use one type or another type of splitting criteria. So you're going to have to work with the people that are experts with that to help you understand what the best is with that. So another type of analysis that we can use is the cluster analysis. And this, I find, is kind of interesting, where you've got, you're looking for kind of groupings, you're looking for what they call it, natural groupings, and how things kind of fit together. And you can really see some interesting patterns here when this is graphed. This is also known as segmentation, so you'll be able to see that in an upcoming couple of slides here. And this is unsupervised learning. So you can pretty easily see how things fit and group together when we do this. So let's go on here. So the results of cluster analysis might be used to groupings of customers. So this might be, okay, so Charter has this group of customers in Minnesota, and they say the most profitable ones are in these areas. That might be the area code, it might be a zip code, it might be a type of service, whether it's phone or internet or cable TV or whatever it is. So you can kind of group those things pretty easily with a cluster analysis. Let's see. With cluster analysis, you really decrease the size and complexity of the problems. So oftentimes you can get things pretty sliced and diced, pretty thin. With cluster, you can say, I want 3 clusters or 4 clusters or whatever it is, and just let the natural let the chips fall where they may with that. It's also pretty easy to identify outliers. So in other words, if we did the Minnesota Charter customers, it'd be pretty easy to see somebody in Wisconsin, they don't really fit here at all. They're pretty easy to cut those out. So with cluster analysis, there's some statistical models where and methods where you can do so hierarchical and non-hierarchical, where you have, and here we're using K again, so how many different clusters do we have? So how many means do we have? How many K means that is? How many K modes do we have? And again, we can kind of adjust that. It's one of those knobs and dials with cluster analysis to find out how the data looks when we're all done. We can also use neural networks, and that's kind of it's a newer way to work through data. So neural networks are kind of an AI technology that helps look at the logic and make sense of it and then present it back to us. There's also fuzzy logic and genetic algorithms, and those also help. Again, in different cases, they may be more helpful to look at the data in different ways. So again, it depends on the type and the size of the data to really pick the best method. Or maybe you do 2 or 3 of these and find out which helps tell the story or tell the analysis the best way. So again, here's one of those questions: how many clusters do you make? Is it 2, 3, 4, 5, 10? There really isn't a truly optimal way. So you have to use some heuristics sometimes to do that. So again, maybe you say, give me 3, then okay, look at the data again, give me 4. This can take time. This can take days of computing to figure out what works the best. So you want to really make the best use of your best guess first, based on what other samples you might have. Okay, so the k-means are, so the k is the number of clusters. That's what I'm trying to get to before. So again, do you want 3, 4, 5 clusters? How many do you want? And again, you may not be able to tell immediately just by looking at it, so you have to, well, generate k random points as initial cluster centers. So maybe you just try it and see what happens. So I want to show you a diagram on the next slide. You kind of see how this kind of shapes out here. So we're going to just do steps 1, step 2, step 3. So just kind of look at those right now. I'll flip the slide in a second. So here we've got these seemingly random samples of data, and as you can see from 1 to 2, it depends, let's see, where our focus is. Okay, so we've got different colors of dots. So in step 1, they're all the same. That's like 1K. And in step number 2, looks like we've got 5 different Ks, because we've got that pink color, the green color, the black, the red, and the blue. In step 3, it looks like we go the same, but we're trying to figure out what group they belong to. Okay, so looks like they're all fully matched in step 3, but we may want to go down to 2, or maybe we want to go to 6, and then we can say, okay, those points, those 5 points from step 1, how many do we really need? Do we really need 4 groups? Do we need 3 groups? How many? What's our K when we're done? Another type of method we could use is association, and so this is also unsupervised. There's no output variable. Sometimes we do a market basket analysis, and so in economics, a market basket is we just take kind of a sample of. So we go to the grocery store, a loaf of bread, gallon of milk, variety of products, and we take a sample today. What's the price of each one? Take a sample in a month from now. What's the price of each one? What's the price in 3 months? What's the price of each of those things? We have a market basket, so we just have a sum of different but kind of related products together, and then we can kind of get a trend on how it looks. And eventually, at the last bullet here, a relationship between diapers and beers. So you can imagine if we did this market basket with a variety of products, including diapers and including beers, I suspect that you could find a pattern at some point. It's interesting, although it may have nothing to do with each other. This is one of those data samples which may come up interesting. You never know. So there we are. So in association rule mining, we have just basically point-of-sale transaction data. So again, if you had 10 billion rows of data, so every point-of-sale transaction that Best Buy has could be input to association. Then output could be affinities among things. So if Best Buy had 10 billion rows of data of point-of-sale, you say, well, people that bought a computer also bought a printer, or people that bought a laptop also bought a USB cord, or people that bought a home stereo bought speaker cable. And I'm pretty sure those associations come up pretty quickly when you see that. And so the example here is a customer who bought a laptop and virus protection also bought extended service plan. Well, Best Buy's going to push it on you, so you don't have much choice sometimes, but whatever. Let's see. So how do you use that information about things that are sold frequently together? We've seen it on Amazon. They put the recommendations right there on the web page for you when you put something in your basket, and you just look at the things. They also suggest here they put items next to each other, a kind of easy shelf placement. You might promote them, put them on sale together, or sometimes you want to put them further apart from each other because you know they buy them together. This forces the customer to go on a little treasure hunt. And boy, that drives me crazy, I'll tell you. All right, so again, here in business, there's an example of cross-marketing, cross-selling, how you do your e-commerce site, again with Amazon, how they recommend people also bought ... In medicine, you may see relationships when you've got these type of symptoms, these things we've seen before, and certain diagnoses and other characteristics, maybe there's a relationship that when somebody does these things or traveled to this country and took this medicine, these things are common output. So there's lots of ways to use this type of association rule. So again, back into some math. Sometimes association is of no help at all. Actually, I've got a book. I might bring this to class and just show you some of these weird associations of how things fit together. They may have nothing to do with each other. They may be purely coincidental, and some of them are downright funny. So again, I don't really care much about the math behind this, but it is kind of interesting to see how this could fit together. So a couple of different algorithms for generating association rules. The algorithms help create frequent item sets, and then they convert to association rules. So there you go. I'll go through each of these algorithms. Let's see. I'll just let you read through that, and then there's a diagram here next. So again, we're trying to break it down into what's the most common association between them. I'm not exactly sure how this is helpful just from the diagram. Let's see. Back. Okay, so they have a minimum. Okay, well, read through this. We can talk about this in class as well. Just want to go through a couple of these there's a couple of slides left here. Some tools that we might use. So some of the engines, so Apache Hadoop, HBase, Pig, and Hive. There's a pretty big number of those in use. Amazon Web Services, I'm sure you've heard of those guys. They do lots of platform as a service kind of things. NoSQL is a pretty big database. Other Hadoop tools and such. So these are some pretty big applications. When you've got hundreds of web servers or hundreds of big data sets, that's where the tools you're going to use. Some of the analysis tools that you might use. In my stats class, we used R a lot. It's just called R. Really handy tool. Not very big, very basic text-based tool. Boy, you can put a lot of data through that thing and do some real nice stats data through there. Of course, you've used SQL before. You've probably heard or used Java in programming, or at least as a consumer anyway. Other programming languages down below there. So kind of interesting to how data can be analyzed and sliced and diced there. All right, so next I'm going to do some myths on this slide. So data mining is not going to give you anything instant. This all takes time and does take analysis. And again, it takes a machine to help crunch the numbers, but a human to make sense of it. Another myth is that it's not yet viable. Oh, by no means. It is absolutely viable. It absolutely is a great tool. And as it becomes more popular and as machines get more powerful and we have more data, it becomes even more viable every day. So even the smallest companies can take advantage of some data mining and understand how it can impact their business. another method requires a separate database, and that's not the case. You can usually use your data warehouse, or you can pull a data mart to do analysis if you want to. And again, that fourth one can only be with those at advanced degrees. That's certainly not true at all. As we heard earlier in this slide deck, it's designed for folks that don't have that kind of background. It's meant to be easy to draw some analysis. And I'm betting if you've gone in, and it looks like most of us have done the SAS visual tool, that you guys don't have a degree in advanced data science. You can go in and draw graphs and make things look pretty. Now, granted, we're just fooling around with it right now, but still, you drag and drop and the data's there and it's good. It's not that hard. It's only for large firms, definitely false. Anybody can take advantage of it. And good old statistics is another name for it. Yeah, that's definitely false, because there's a lot more going on here than stats. There's a lot more pieces of data we can use and analyze and go through. A couple of blunders. I think these are really related to what we just talked about in the previous slide. So yeah, you want to take the time, don't be sloppy. I think that's somewhat common sense. Might be more, again, more in book number 6 there. So, and that's the end of this chapter. All right, chapter 6. Here we go. We're going to the predictive modeling chapter. So here we're going to go through ANNs, or the artificial neural networks, and also go through SVM, which is support vector machine. Support vector machines, and kind of go through what the differences are and kind of how this is different from biology versus machine learning. Kind of go through that as well. So also go through the 2 SVM versus ANN. Go through some of that k-nearest algorithm again, a k-nearest neighbor. So we'll see some of that k pop up again. So a little bit of math in there, but it won't be too bad again. And then we'll go through pros and cons, etc. So not too bad. So neural networks all by themselves are a metaphor for how humans use brains to work through information processing. And so we think of neural computing as something that mimics the brain. So artificial neural networks are exactly that, where they can be used for pattern recognition, some forecasting prediction, some of those things we were talking about in the previous chapter. And the business areas are in finance, marketing, manufacturing, etc. So we can take advantage of this ability for a machine to think like a human, or to associate things like a human, and then be able to present it to us so we can better understand what's going on. So in the biology world, how brains in all kinds of animals work is we have these different pieces of so all the synapse, somas, dendrites, axons, etc. And then we're going to associate this with how it works with an artificial neural network instead. So we got 2 brain cells, 2 neurons connected together, and data, pulses, electricity kind of gets fed between them. And the signal is how we, as humans and as other creatures, try to do thinking and sorting and logic, such like that. So in a ANN, obviously it's different, it's mathematical in nature, because that's how processing works. And but there are things that we can put in here that make it look very similar. So even though they're different, we can still have inputs and outputs. We have we can weigh the inputs. So we have what strength or what value they have. Do some transfer of it, an f of x, or in this case an f of s, and then have the outputs and find out what we want to make out of that. So the table here, side by side, again, we've got those biological terms on the left side, and on the right side we've got the artificial side. So you can think of computational things on the right-hand side. And slow versus fast, well, that's relative, I guess. We've got obviously a lot more neurons than artificials do, because that's just what we had been able to work with so far, but oh well. So some of the basic elements here, we've got the processing element and architecture and information processing. So I think this will be somewhat straightforward. In the network architecture, there are some hidden layers, some things that are not obvious or they're not visible, and we may not even care about them all necessarily. We can do things in parallel, so that's good to know that we can have multiple things happening at once. Yeah, we've got inputs, outputs, weights, and then it's kind of summing going on in the middle. So I'll get the next slide here and look at this. So again, we've got these different layers, and PE is our processing elements. And we kind of see how they relate together. Got a hidden layer in there that may not get visible, etc. And then now we've got those inputs up here with our x sub 1, 2, and 3. We've got a kind of a weighted sum in there. We've got a function going on in there. We have the output. So where does this stuff come from? Well, all this can be put together a number of different ways, and we're not going to get into a ton of details, but we certainly will be able to at least look at this like, oh, I've seen that before, and can make sense of some of it anyway. So this is a network with one hidden layer. And on the next slide here, we've got a summation function where we've got, looks like they're putting some values in, we're weighing them. So in a single neuron, in sample A here, we put a weight on them, and then we're having our processing element, and then the output of Y. We've got multiple neurons with our sample B up here. Again, we've got some X inputs, X sub 1, X sub 2. We've got our various weights in there. We've got our processing element and our outputs. So this is, for me, it's a bit to take in. It's a bit to bite off here to all just look at it once. But I mean, it's a mapping. It flows. I don't know what the functions are. I don't know what the math is inside there, and frankly, I don't care right now. And as an end user, I wouldn't care either, but I want to be able to get to the output. So what are the inputs, what are the outputs? And the middle, to me, is kind of like a black box, which is kind of good to see kind of under the hood about what happens. So our transformation or transfer function here is what happens. It's kind of our, what's the important part of the processing. So again, we've got the X values, the inputs on the left side. We've got our weights that we assign to them. So in other words, how important or how significant are each of those inputs. And our processing element happens in the middle. We have our output. In this case, it is linear. So the bigger the X, the bigger the Y. If it was not, you could have a variety of different types of functions. So sigmoid or tangent, hyperbolic are other types that it could be. Frankly, I'm not an expert with this, so I'd have to do a little more digging to understand exactly how they are different. But it's good to know that it doesn't have to be just one type of a function that can go in there. Different type of neural network architectures. They can be set up to specify classification or work through regression, or work on clustering, just general optimization or association. So those different types we talked about in the last chapter. The most popular is a feed-forward, multi-layer perception with back propagation learning algorithm. Well, that's kind of a mouthful. I suspect that's pre-built. We've got some scientists that's figured out the best way to use this. We'll take advantage of it, and that works for me. There's also other types of network architectures too. We're not going to go through too many of them, I don't think. So let's go to a diagram next here. So here's that feed-forward multi-layer processing with one hidden layer. So again, we've got our inputs on the left side, they're the red dots. That middle hidden layer, which we don't see, we don't exactly know what's going on, they have an output layer. So we have to let the machine kind of figure out how they are relating. And then, so here we have predicted versus actual. So again, we've got our 2 points there. And let's see. So our output is the blue on the right-hand side. Let's see. So we don't have anything that goes directly from the left to the right. It all has to go through this hidden layer in the middle. So we really don't have, dare I say, any visibility to this, but what the hidden layer does, which is fine. I just want to point that out. Versus the next slide where we've got some loops that go around and kind of feed back and forth. So we have a couple of different outputs here based inputs, some hidden here, and then so these two are hidden here, and then these are the outputs right here. We also have some other artificial neural networks with self-organizing maps. So basically, each of the inputs has a link to each of the middle layers, and this is kind of like a mesh kind of a setup. You can see each of the middle layers has 3 inputs to it, so this kind of shows all of the possible outcomes. We call this a self-organizing map. I don't really see how this is helping us right now, but the machine can use this as a learning type to kind of get all the possible samples that are out there. Here's another type of diagram where we have inputs and outputs. They're highly interconnected, so each of them crosses each of the others at least once, and itself. We have each of the possible combinations as out. I'm kind of seeing this from patterns I can develop here. All right, so with our development process, we had that previous data mining, had several steps there. Here's kind of what it looks like for a neural network, an artificial neural network. So we get the data, reformat it, separate it, choose an architecture, work through an algorithm, change the parameters to our liking, set our weights, kind of go through all of this. So obviously this is a pretty rigorous process. So for a person to understand this, they pretty much have to have a data science background to go through and know which things to use. So this would take a little bit of practice if I was going to write this from scratch. Again, likely I would probably have a tool that has this and walk me through a widget step by step and understand what the best way to do that. And I might do this 2 or 3, 4 different ways just to get the outcome that I'm looking for. All right, so here are an example. Here was looking at the different ratings of movies and how they can fit together and all the different categories on the left side as inputs. And then we've got a couple of hidden layers in the middle. Again, we're not really sure what these do. As an outsider, we don't understand what they do, which is fine. And then on the right-hand side, we've got the outcomes of where the movie will end up. So again, we're showing 7. That could be 700 here on the left as inputs. Then these hidden layers might be things that happen with each of those types. It might be geography. It could be other things that are layers we don't understand or see or associate with. Then the outcome, also the possible outcomes on the outputs on the right-hand side in the red here. So obviously we want to have what's going to be the most likely. So they're going to, what is the likelihood of a 9 versus a 1? So obviously a 9 is great, but I mean, where's it going to land? The day of the week, the time of the year. These could all be layers that we don't have any any say on. So there's just stuff that's been used in the past. So there we go. All right, so here, instead of data model, with our ANN model, we've got data split into 3 parts. We've got training, validation, and testing. So the training is kind of learning what those layers should be, whether they're hidden and such. Validation will tell us if we've got it right, and we actually use 20% of the data to do the actual testing itself. So that's if we have all of the data. We also use k-fold cross-validation, where we only take a limited sample of the data. We have less bias, but it is more time-consuming. And we do it in multiple waves for the k-fold. All right, so this is walking through a supervised learning process to make sure the weights are correct and output is achieved. Okay, that's good. So this back propagation learning was something we mentioned in an earlier slide. So kind of goes through the process of what this means. And again, this is a fairly intense 6-step program, where 6 go back to the top again, make sure we have things stabilized. And I don't think off the top of my head I would know, if I was just walking into this without a data science background, I'd know what to set. I'd want to be able to have some guidance on this. So again, this is the person helping to write or to program the algorithm, and you'd want to tweak this to your liking and find out what might work the best. If I was going to do this from scratch, I would find out what was used in the industry, what's been used previously, and kind of start with that. I'm going to have to tweak it one at a time, kind of rerun it again and again and again to get kind of what I'm looking for to make it pop out. All right, so the common criticism is lack of transparency, explainability. Remember those hidden layers? It's kind of hard to work through that because you couldn't really see it. So one of the problems is it's a black box. In other words, you have inputs, you have outputs, you have no idea what goes on in the middle. So you can do what's called a sensitivity analysis, and you do this on a trained artificial neural network, and you have inputs, outputs, and you have results that illustrate the relative importance of input variables. You can have each of the inputs, and again, so the weight is set certainly, but you can have what's the relative importance beyond the weight for impacting the output. That's one way to kind of overcome that. So in this case, for sensitivity analysis, we have systematically perturbed inputs. In other words, we vary them somehow, we change them somehow, and we look at the observed change in the outputs. So the same inputs just change somehow, and then we've got the outputs, and we also measure that change, so that delta on the right-hand side. So now we're going to move into SVM, or support vector machines. Another machine learning technique, usually used in linear models. It's also capable of doing nonlinear relationships, forcing them into a linear fashion. Let's see, they're closely related to artificial neural networks, but they are different. So the goal of SVMs is to generate mathematical functions that map to input variables to desired outputs for classification regression type. So in other words, you're going to have an f of x when we're all done with this. So we use nonlinear kernel functions, and we do a transformation. So if you've done any kind of linear algebra, transformations are exactly what happens. You have an f of x, and you have this plot on the graph, and you just change that with your transform function, and then you see the new output when it's finished. That's basically what SVM helps us do. We have some linear function. We can just use this transform function on there, and the new output is shown based on the new input. So it's a pretty solid. And again, it has solid mathematical foundation. So as I mentioned earlier, hyperplane. So it's just we're going to plot this on a graph, and we're going to show an axis, and we're going to look at the separation space and see how basically visually see how this comes out. And of course, it's good for humans to look at it, but it's better for a machine to analyze it and show us kind of what the data actually means. And let's see. Kernel function uses the kernel trick, which is a method used for linear classifier algorithm to solve a nonlinear program. So, yeah, so sometimes you have nonlinear functions. So obviously linear algebra, you can't use to do nonlinear problems, so you have to kind of force it into linear by doing a little bit of a trick on it. So let's look at some examples here. So we've got a couple of different, on the left side, we've got a couple of different L values here, L sub 1, L sub 2, L sub 3. So those may be trend lines, those may be regression lines. I can't really tell just basically by looking at this. You see how they overlap, they intersect a little bit. We may want to force those to be parallel, and then we kind of measure how they are spaced or what impacts them. So we can kind of play with our function, play with our variables a little bit to make sure that they line up, and then measure how what we change to make them line up. All right, so how does it work? So number one, you pre-process the data, so back to that scrubbing, cleanup of the data, and then you develop a model, and the kernel type is the basic one. RBF is the most obvious and the most common kernel type that we would choose. Choose your parameters, and then you look at the results and find out if that works or not. And most likely you go back to the drawing board and just change some variable, change some of the inputs, and make it work for you. So here's a kind of a diagram of how we go through this: is pre-process, develop, and deploy. I suspect this is also in the chapter. All right, so where do we use SVM? Kind of across the board, whenever we can apply a linear model, even some non-linear models, this SVM will work fine. We can use them for comparative studies over time, so whether it be a certain market for manufacturing or natural resources or any kind of those different kinds of markets we could do. And yeah. So we can use the K nearest neighbor, or KNN model, and we can kind of find out how things are clustered together, kind of how they work together. So K equals the number of neighbors that we use, and the best way to do this is just to look at the graph. I'm going to show you the next one here. So if we say we have a K equals 3, see how we look in the middle there, so there's only 3, so we draw a radius, and we can see the 3 closest fit in that model with a KNN. If we do a K equals 5, we have to draw a slightly bigger radius to get additional units into there. So you see how we're using how big of a K depends on how large of the radius we need to draw. So I'm going to go back to the previous slide. It's a simplistic and logical prediction. Let's see. It's going to show us how big of a K we should use for that. Again, we have a training set and a validation set. So training, we're not using it for the real model. We're just kind of getting up to speed on how the model should be used. The validation set helps do that. We can actually use the new data for predicting and going forward. So see how we use data really for consumption to learn and to get better and validate our techniques work from historical data, take new data and actually predict and forecast from it. Okay, here's the math slide. Don't worry, this is not on the test. I just want to go through some of how the math looks and how it works. It's really not terribly crazy. It could be done in a graphing calculator pretty easily, but I'm not going to expect you to go through this. Just know that there's math behind this, how we do the distance metric. We can calculate the value of what our K is or what it should be for an optimal value. We can also do cross-validation to determine the best value for K and the distance. And that is the end.